Power regression asks the question, what power function fits best? Before we get into our data and our example, I have found that a lot of people are actually not quite sure what I mean by power function and what do they look like. So power function in its simplest form is just y equals x raised to the a, some power on the x. And you're familiar with some of these, I'm sure. Quadratic, cubic, quartic. Now we can make it, of course, a little bit more complicated with vertical and horizontal shifts and coefficients in front. We'll get there eventually, but not quite yet. We're actually going to keep it a little simpler. And we're going to deal with just an exponent with a coefficient in front. That's going to be our basic power function. And of course, it's going to get a little bit more complicated because we can use decimals for the exponent. We can also use decimals for the coefficient. And so we're going to get something that looks kind of like this. And a lot of people aren't quite sure what that looks like. So there are different ranges, different behaviors for each range, depending on whether the exponent is bigger or equal to 1, between 1 and 0, or less than 0. These are, of course, the negatives. What I can do is show you them one at a time. So when a is bigger than 1, this is a graphing program online, desmos.com, an awesome program, I recommend it, where I have a as a slider. I'm going to slowly increase it, and you'll be able to see what it looks like as I play this video. So you can see over here the slider is increasing. It started at 1. The shape is alternating between the classic quadratic parabola bowl shape and the classic cubic sort of S-type shape. Right? As the exponent gets bigger, it gets more flat-bottomed. Right, there's the cubic. And there are times where this side doesn't exist at all. That's like when there's a square root. You can't take the square root of a negative number, so that side disappears. So that's when a was bigger than 1. If a is between 1 and 0, we actually get a different kind of shape, which looks kind of like this. Right now I'm starting at 1 and sliding backwards. And you can see we're getting kind of this square root shape. Right? Again, there are times where it's on the negative side, it's down or up, and sometimes it doesn't exist because of that square root issue. And as we get close to 0, of course, we're going to end up with a horizontal line at 1. Because anything raised to 0 is equal to 1. So we have that kind of behavior. What happens if a becomes negative? So again, here I'm starting with a slider at 0. I'm going to be sliding it back towards negative. There we go. Here we are at 0. And now, of course, negative means reciprocal. So we're getting the classics of 1 over x squared kind of behavior. Yet again, it's flipping positive and negative on this side and sometimes disappearing completely. So really, with power functions, we have a wide variety of behaviors, which makes it very, if you excuse the pun, powerful, because we can model a lot of different shapes with one function. And there's -3, and that's what power functions look like. All right, so now let's look at our example. So we have the same set that I used for exponential, right? Because I can, just like linear and exponential, you can do a power regression for any data set. It's whether it actually makes sense or not, or is the best fit, but you can do it for any data. All right, now as I said last video, we're going to transform by taking both the log of the x and the y for power function. Again, in an idealized power function, that would make it perfectly linear. Again, this data is probably not an ideal power relationship, so it won't exactly look linear when you do that, because we'll graph it. And it looks something like this. And then we'll do the same procedure we did for exponential. We're going to find the linear regression for now x and y, which is an L3, L4. We use the linreg, and we get our linear regression. The process for converting back to non-log form, which will be the power form this time, is the same, 10 raised to both sides of the linear regression. 10 raised to log y hat is just y hat. I'm using the laws of exponents backwards again. Now this place, I'm going to do something a little different. Where before the x I brought to the exponent, here I'm going to bring this number out as the exponent. It's going to look something like this. Because 10 raised to the log of x, of course, is x. And we have our power function. We should probably graph this over the original data just to check. And it has something kind of like that. Now, what we should also do is, I'll show you how to do this on the graphing calculator, which you can see in my stat calc menu. A is power regression, so I can actually go alpha A if I wanted to. Now I do the original data, L1 and L2, and I should get the exact same equation as this, which I do.